And now let's have a look at some formal tests. And the first test that I would like to present is called the Park test. And it involves two steps. So first of all, we need to run the Euler's regression disregarding the heteroscedasticity and obtain the estimated residuals from this model. After this, we run the following regression. So we take the natural logarithm of squared residuals and we regress it on the intercept on the natural logarithm of our independent variable. And the decision rule is the following. So if beta, the coefficient, is statistically significant, so if it is different from 0, then we say that there is heteroscedasticity in the data. However, if beta is not statistically significant or it is statistically insignificant, we say that there is homoscedasticity in the data set. However, this problem has a very big limitation, and it has to do with the error term from equation number 3. It might happen that the error term will not satisfy the Euler's assumptions and may be itself heteroscedastic. And because of that, this regression is no longer valid and the value of beta coefficient is no longer valid. To deal with this problem, Glejser has developed another test, and it's very much similar to this test. However, as you can see from here, the number of regressions that can be estimated is quite big. So let's go to the first step. So we run the Euler's regression disregarding the heteroscedasticity and obtain the estimated residuals. And after this, we need to run one or more of the following regressions. So we take now the absolute value of the error term and we regress it on the independent variable, or we regress it on the square root out of the independent variable, or we regress it on the ratio of 1 over the independent variable, or 1 over the square root out of the independent variable. Or we do the following: we take the square root out of the first two terms, and the last equation is we take the square root out of the first two terms, and x, the independent variable, is also squared. So this is the procedure, and the decision rule is the same. So if beta 2, so the coefficient at independent variable, is statistically significant, then we say that there is heteroscedasticity in the data. However, if beta 2 is not statistically significant or it is statistically insignificant, we say there is homoscedasticity in the data. Unfortunately, this test also has a number of limitations, and once again, the error term from these regressions might not satisfy the Euler's assumptions and may itself be heteroscedastic. And because of this, the estimation result that we get from these regressions are no longer valid, and we cannot be trusted. So in a sense, the value of beta 2 can no longer be used for the interpretation of the presence or lack of heteroscedasticity. And another problem is equation number 8 and equation number 9. So the last two equations, as you can see, they are no longer linear in the parameters, right? Because now we have the square root out of beta 1, the square root out of beta 2, the square root out of beta 1, the square root out of beta 2. So those models are no longer linear in the parameters, and therefore they cannot be estimated with the usual Euler's procedure. So the Euler's procedure that we are practicing during this semester. So to be able to estimate this type of models, we will need some other statistical econometric tool, which is out of the scope of this module.